Determine the point of intersection of the lines with the equations y is equal to 4x minus 32 and y is equal to minus 6x plus 8. Okay, well, we'll just set them equal to each other, and that should allow us to get the point of intersection. So 4x minus 32 is equal to minus 6x plus 8. So that leads me to, I believe, 10x is 40. So x is 4. And if x is 4, sub it back into either one of those to get the value for y. And when you do, you'll get y is equal to minus 16. So that point of intersection will be 4 minus 16. Suppose that a is an integer. Determine the point of intersection of the lines with the equations y is equal to minus x plus 3 and y is equal to 2x minus 3a squared. The coordinates of this point will be in terms of a. Okay, so same kind of story. Set them equal to each other. Minus x plus 3 is equal to 2x minus 3a squared. And let's see, if I solve here, I get 3a squared is equal to 3x minus 3. So that means a squared would be x minus 1. So that means x is equal to a squared plus 1. And then I guess I just substitute back into either one of these to get y. And if I do, I get y is equal to minus a squared plus 2, I believe. Yeah. Okay, so then my point is a squared plus 1 and minus a squared plus 2. Okay. Part C. Suppose that c is an integer. Show that the lines with the equations y is equal to minus c squared x plus 3 and y is equal to x minus 3 c squared intersect at a point with integer coordinates. So let's set them equal to each other. And then let's see here. 3 plus 3c squared. And then let's put the x's all on one side. X plus c squared x. Factor out an x and get 1 plus c squared. Oh, okay. Factor out a 3 and then we get 1 plus c squared. So then, oh, that's interesting. The 1 plus c squared cancel on both sides, these two guys. So x is 3, and then substitute that back into, I guess, any of these to get y, and we'll get y is equal to 3 minus 3c squared. And, well, this is an integer, and since c is an integer, that means y is an integer also. So we have shown that the intersection point, which is 3 and 3 minus 3c squared, is indeed does indeed have integer coordinates, because this is obviously an integer, and this is an integer because c is an integer. Part D. Determine the four integers d for which the lines with the equations y is equal to dx plus 4 and y is equal to 2dx plus 2 intersect at a point with integer coordinates. Okay. So we do the same thing, let it equal to each other. So we got dx plus 4 is equal to 2dx plus 2. So let's see here, 4 minus 2, let's put the numbers on one side, 2dx minus dx. So that's just going to be dx is 2. So therefore x is equal to 2 over d. X is equal to 2 over d, okay? So since the intersection point has integer coordinates, that means x has to be an integer. And the only way x can be an integer is if d divides into 2. So d can be either plus or minus 2 or plus or minus 1, I guess. Yeah. And then if that's the case, then x will be 1, 2, negative 1, negative 2. And then y will also be an integer since d and x are integers. Okay, so what are they asking for? Determine the four integers. So these are the four integers right there. Suppose that A, B, C, D, E, F is a regular hexagon with side lengths 6. Each interior angle of A, B, C, D, E, F is equal to 120. Part A, a circular arc with center D and radius 6 is drawn from C to E. Determine the area of the shaded sector. So here is the diagram for the part A. So let's work with that diagram. Let's move this up here. Okay, so what are we trying to do? Shaded region. Okay, so the area, did they tell us anything? Well, yeah, this is 6, and, well, this is 6 sides, so that's going to be 120. Did they give us that, or, yeah, they did. Each interior angle, yeah, they already gave us that. Even if they didn't give us that, if it's a regular hexagon, you can figure that out, actually. For any kind of polygon, you can always figure out the what the interior angles are pretty easily, with the fact that triangles have interior angles that add up to 180. Okay, so the area of the shaded region, we'll just call it SA for shaded region, will be pi r squared, right, which is the area of a circle, but we're only taking 120 degrees of that circle. So out of the full 360 degrees, you're taking just 120 degrees. So it's a segment of a circle. Okay, the radius in this case is 6, and this is just 1/3. So this is going to be 36 divided by 3, so that's 12. So 12 pi is the answer for part A. Part B. The circular arc with center D this time, and radius 6 is drawn from C to E. As shown, a second arc with center A and radius 6 is drawn from B to F. The arcs are tangent, and at the center of the hexagon, line segments BF and CE are also drawn to determine the total area of the shaded regions. Okay, so same kind of thing, but slightly different. So I will call this segment A, like that. So A, just sort of to explain what it is, it's that segment, or sector I should say, like what we did in part A. This was a sector, or you can call it a pie, or whatever you want to call it. I call it a sector. And from it you subtract a triangle. So basically you're going to take the whole sector like that, and then you're going to subtract from it this triangle, which I'm drawing in green. And if you do that, you will get A. And then at the end, we'll just try to figure out 2A, since they want both A's. Okay, so the sector shouldn't be that hard. We already did that, actually. Pi r squared times the internal angle, which is 120. 120 over 360. And then the triangle, okay, triangle, I'm going to need a little bit of time to figure that out here on the side. Let me just draw that triangle. Okay, so I'm going to draw a little line perpendicular. So this is 6. That interior angle was 120, so that means this is 60, that's 60. And that line, since it's perpendicular, then that's 30. So this is a 30, 60, 90 triangle. Now 30, 60, 90 triangles have the ratio of the sides. Let's see here. If I were to take that 30, 60, 90 triangle, this guy, well, this is 90, that's 30, and that's 60. The ratio of the sides are 1, 2, and root 3. So since this side was 6, we can get the other two sides. That means this side is 3, and this side is 3 root 3, right? 3 root 3. So that means the whole side there would be 6 root 3. Yeah. Okay, that's pretty good. So 1/2 base times height. The base is 6 root 3, and the height is root 3. Oh, no, sorry, the height is this guy, 3. Just 3. Yeah. Okay. All right, so then R was 6, right? Just like the previous question. So that we already did, it was 12 pi. So this is going to be 9 root 3. And then remember, don't forget that we have to actually figure out 2a because we want both of those. So that's going to be 24 pi minus 18 root 3. 24 pi minus 18 root 3. Part C. Along each edge of the hexagon, a semicircle with diameter 6 is drawn. Determine the total area of the shaded regions. That is, determine the total area of the regions that lie inside exactly 2 of the semicircles. We are now looking at this diagram, which is a little bit different, of course. Now I'm going to have to explain this in parts because the diagram is way too small. So let me just draw what I think is part of it. And now what I'll do is I'll draw sort of a, I guess a line between the between that shaded area. So if the shaded area is, let's say, from there to there, just kind of split it in half, okay? And that's pretty much what I've attempted to do. I split it in half. And each of these halves I'll call A. So that one's A and that one's A. Okay, so that's, I guess, part of it. Now, at the end of the day, we have to figure out 1, 2, 3, 4, 5, 6 shaded areas, and each of them I have called 2A. So in total, what I really would have to figure out is 12A. So at the end, I'll do that. Now, I just have to figure out A. So now, how am I going to figure out A? What I'll do is, in this semicircle, I'll draw this sort of the center, and I'll draw a line from the center to the edge right there. And that will create a shape, and that will help me figure out A. So A basically would be the sector minus the triangle. So the sector is basically the whole thing. Let me see if I can put it in a different color so that you guys can see it. I'll choose yellow. So the sector is the whole thing, all the way around like that. That's the sector. And the triangle is basically everything except the A, I guess. So the triangle sort of is that part. So if we can do that, we'll be able to figure this out. All right, so the sector, we definitely need to know this angle here. I'll just call it theta for now. And so it'd be theta over 360 times pi r squared. Now the r, the side was 6, right? So the r, therefore, would be 3, since it's half of the 6. So that'd be pi 3 squared. And the triangle will be 1/2 base times height. And the base and the height, I'm not sure yet. So I'm just going to put it in once I figure it out. Okay, so now I've got to figure out the angle. And, how am I going to do that? Well, let me draw that again because I don't want to make that diagram too messy. Let me draw that again. So if it's like this, and we know that the internal angle, like this guy, whole thing, that whole thing, is 120. Is that right? Yeah, I think that was something we knew from before. So if I want half of that, so if I were to draw like that line again to cut it in half, like, something like that. If I want half of that angle, basically what I'm saying is I want this angle right here from there to there. That's going to be 60. So if I were to draw the center and then connect the dots of that triangle, that's 60. Now this is a radius from here to here, that's 3, and this is also a radius from there to there. So since that's at least isosceles, that's going to be 60 also. Well, if that's 60 and that's 60, then this is 60 also. So I hope you followed how I was able to figure out that theta is 60. So that is pretty good. That's 9 pi. And now we've got to figure out this base times height to figure out the final piece of the puzzle. Now that triangle, I'll just, I guess, yeah, it's an equilateral triangle. So that shouldn't be that hard to figure out the base and the height. If it's equilateral, then, well, the base is 3, and that's going to be 60 degrees, 30 degrees, and the ratio of the sides, as always, is 2, 1, and root 3. So that means that if that's 3 there, then we have the height over, let's say, 1. The height over 3 is the equivalent of root 3 over 2. So the height is 3 root 3 over 2. If I have done that correctly. I believe I have. Okay, so the 1/2 base, put 3 there, and the height, 3 root 3 over 2, and off we go. Okay, so this will be, that's 1/6, so 9 over 6, which is 3 over 2 pi. And this looks like it's going to be 9 root 3 over 4. Yes. And that's A, but I want to figure out 12A. So 12A, if you multiply through by 12, will make this 18 pi, and 12 divided by 4 is 3, so 3 times 9 is 27. So there you go, 18 pi minus 27 root 3. Suppose that f at x is equal to x to the power 3 minus px squared plus qx, and g at x is equal to 3x squared minus 2px plus q for some positive integers p and q. If p is 33 and q is 216, show that the equation f at x equals 0 has 3 distinct integer solutions, and g at x equals 0 has 2 distinct integer solutions. Okay, so let's start with the f at x first. And f at x, we have to set to 0. Well, what it is, x to the power of 3 minus p, but p they've given me as 33 x squared plus q is 216x. So that's going to be 0 is x to the power of 3 minus 33x squared plus 216x. Okay. Well, let's see if we can figure this out. If I factor out an x, this will be x squared minus 33x plus 216. And I think I can factor that a step further. Let's see here. 27 and 6 I think would do it. Minus, minus. So the roots are 0, 27, and 6. And that's 3 roots. And that is what they wanted you to show. Show that f at x equals 0 has 3 distinct integer solutions. Got to do the same kind of thing for this time for g at x, and g at x is 3x squared minus 2px, so that's 2 times 33x, and then plus q, so plus 216. And then same thing, set it equal to 0. So this will be 3x squared minus 66x plus 216. I think we can divide through by 3 and make that x squared minus 22x plus 72, and I think that factors really nicely. So let's see here, 18 and 4, I believe, yeah, 18 and 4, that'll work. So that means x is either 4 or 18, and that's 2 roots, or 2 solutions. Yeah, 2 solutions, and that's exactly what they wanted us to show. Suppose that f at x equals 0 has 3 distinct integer solutions, and the equation g at x equals 0 has 2 distinct integer solutions. Prove that p must be a multiple of 3, q must be a multiple of 9, p squared minus 3q must be a positive perfect square, and p squared minus 4q must be a positive perfect square. Okay, well, I think we have to take this one step at a time, so let's see what we can do. First, let's start with f at x. And that is x to the power of 3 minus px squared plus qx. Now, they haven't given us any numbers yet. For last time they gave us values for p and q, but this time they're not. Okay, not a problem. This is going to be set to 0, right? So 0, and then factor out an x. That'll be x squared minus px plus q. Okay, so if this has 3 integer solutions, that means that, well, this is going to give me one integer solution, namely x equals 0. So if I want 2 additional roots from here, that means when I do the quadratic on that one, the quadratic being x squared minus px plus q is 0, that quadratic has got to give me 2. And the only way it's going to give me 2 is if the discriminant is greater than 0. Because if it's less than 0, it would not give me any integer solutions. If it was equal to 0, it would give me just 1. So if I did the quadratic, it would be p plus or minus the square root of p squared minus 4q, right? All over 2. So we want the discriminant, which is what's under the radical sign, minus p squared minus 4q. We want that to be greater than 0. But in addition to having 3 integer solutions, well, in addition to having 3 solutions, the solutions have to be integers. And the only way that's going to be this whole thing, the only way it can be an integer is what's under the radical sign is a perfect square. So that means p squared minus 4q has to be some perfect square, like n squared. So I think that actually solves solves part of this. It solves this part. Yeah, so I'll just put that there. 4 has been shown, but we have to now show the other guys too. That's the only one of those 4 that I've shown so far. So I've got to still show that, 3, 2, and 1. Okay, so let's see what I can do with g at x. G at x, if I recall, was 3x squared minus 2px plus q. And that's being set to 0 also. And same kind of thing. We want 2 integer solutions. Okay, so I'm going to pretty much do the same kind of thing that I did previously. I got to look at the quadratic. So if I do that, it'll be 2p plus or minus square root of 4p squared minus 12q all over 6. And then I think I can factor out a 2. So that will make me p squared minus 3q under the radical all over 6. So kind of same thing as I did here. In order for this to be 2, which is what we want, the discriminant has to be greater than 0, and the discriminant has to be some sort of perfect square. So let's just say m squared. And that takes care of part 3. P squared minus 3q has to be a perfect square. Okay, that makes sense. So now I guess we have to prove 1 and 2, these guys, and that will allow us to complete the question. So let's see how we can do that. We have to then, let me look at g at x again. So g at x is 3x squared minus 2px plus q, correct? Now I'm going to divide through by 3 here, and that'll just leave me with x squared minus 2 over 3px plus q over 3. Now, you all remember Vieta's, right? Vieta's formula that allows you to look at the sum. If you have, I think it was ax squared plus bx plus c, the sum of the roots in that equation can be calculated as b over a. Now, if you apply that to here, that minus b over a would be, I guess, 2p over 3. And the product of the roots, according to Vieta's product of roots, is, I believe, c over a. And if you apply c over a to this guy, it becomes just q over 3. Now, since the roots are integers, correct? Yeah, they're integers, distinct integers. Then the sum of 2 integers, the sum, would also be an integer. So therefore, the only way that can be true is if p is a multiple of 3. So we'll just call it 3 capital P. And same thing, if you have 2 integers, the product of those 2 integers will also be an integer. So the only way that's true is if q is also a multiple of 3, so we'll just call it 3 big Q. So those are 2 very important findings that we have to make a conclusion for. Okay, so now where do we go from here? I think we can just go back to what we already found out, which is that p squared minus 4q is some sort of perfect square. Now, I'm going to substitute these guys, and if I do, I will get 3 big P squared minus 3 big Q is some sort of perfect square. So that's 9 big P squared minus 12Q, right? 9, yeah. And then if I factor out a 3, this will be 3 big P squared minus 4Q is n squared. All right, so well, the only way this will be a perfect square is if this is a 3, so that in the brackets also has to have some 3 in it. Yeah. So it's got to be some sort of multiple of 3. Yeah. So I think the only way that's possible is that both of them are multiples of 3's. So that means 3p squared is a multiple of 3, and 4q is also a multiple of 3. So from this one, this was like 3 large p, right? Because we had to put in large p. So this is like 3p times p, like that. And that is the equivalent of small p times big P. And we're saying that is a multiple of 3. So the only way that can be a multiple of 3 is if this is a multiple of 3. So small p, let's see if I can, small p is a multiple of 3. Right? I hope that makes sense. So you got 3k. That's the only way that this can be a perfect square, if that in the bracket is a 3k. And then that means that 3p and 4q both have to be multiples of 3 in order for that to work out when you do the subtraction. And therefore, and remember, this is the big P, and so that's why I broke it up into 2 big P's. And then the 3p here is the equivalent of small p. So this is small p here, and this is the big P. And we're saying that this thing is a multiple of 3. Well, and I think we actually proved point 1, this guy up here, over here, already, that P had to be a multiple of 3. So I kind of already proved it. So I think the only thing left for us to prove is Q is a multiple of 9. That's the only thing left to prove. Okay, so that shouldn't be that hard. So if 4Q is a multiple of 3, and 4Q is equal to 4 times, let's see here. Yeah, I think that's it. If 4Q is a multiple of 3, then that means that Q, this big Q, I'll just write big Q has to be a multiple of 3, is a multiple of 3. So it's like Q is equal to, say, something like 3, whatever, at this point, 3t, let's say. And then going back to here, that means Q is equal to 3 times big Q, which is 3t. So Q is equal to 9t. And that proves that small q is a multiple of 9, which is the last part of the puzzle. So we have proven all 4 things, that p is a multiple of 3, which I proved here, actually. And I think I was attempting to prove it here, but I even if I have not, I've proven it there. And then the second thing, that q is a multiple of 9, which we did here. And then the last two, that p minus 3q must be a perfect square, and p squared minus 4q must be a perfect square. So we've proven all what they wanted us to.